All right, let's dive in. Today, we are tackling one of the most elegant, truly elegant shortcuts in all of physics, electric potential.
So if you've ever found yourself wrestling with an electric field problem, you know the pain, right? You're trying to juggle all these vectors, tracking components in the x, the y times the z direction, and it just gets messy, fast. But what if I told you there's a much simpler, cleaner way to describe the exact same physics?
Okay, let's just break this down. Over on the left, you've got the electric field, E. Now that's a vector, and that means at every single point in space, you have to keep track of three separate pieces of information: how strong it is in the x direction, the y direction, and the z direction. Kind of clunky. But then on the right, we've got our solution, electric potential, V. And it's a scalar. You know what that means? At every point, we just need one single number. That's it. It's an absolutely incredible simplification.
So the big question is, how does this scalar shortcut actually work? Well, it all boils down to two familiar concepts: work and energy. So what exactly is this potential difference? Really, at its core, it's just a measure of energy. The official definition says it's the amount of work you have to do to move a charge from point A to point B against the push of an electric field. It's kind of like the effort it takes to push a heavy box uphill, right? That potential difference is just a number that tells you exactly how much energy you had to spend on that journey. Okay, let's put the math on hold for just a second, because to really get a feel for potential, we need a solid mental model. So let's build one together.
And the best way to do that? We'll start with something we're all familiar with, a force we experience literally every single day: gravity.
Okay, just think about it like this. You've got a massive planet, and it creates a gravitational field all around it. Now, if you want to lift a heavy boulder against that pull, you have to put in work, right? You're expending energy. And that energy doesn't just vanish. No way. It gets stored inside that boulder as gravitational potential energy. And it's simple. The higher you lift it, the more potential energy it packs away.
And here is the absolute key to the whole thing. We can map out this entire landscape of potential energy using a simple topographical map, the kind hikers use. Every single point on that map doesn't need an arrow pointing which way is down. No, it just needs one number: its elevation. And that, my friends, is a scalar field.
And this brings us right to the big reveal. Electric potential is the elevation on an electric topographical map. It is the exact same idea as our mountain. It's just that this landscape is built from electric charge instead of rock. It's simply the potential energy at any point divided by whatever charge you happen to place there.
And check this out, because this illustrates one of its most important properties. Just like when you're climbing a mountain, the total elevation you gain between point A and point B is exactly the same, no matter what path you take. It doesn't matter if you take the long, winding scenic route or the super steep direct one. The change in your elevation, your potential, is identical. It is totally path independent.
Okay, so we have this powerful analogy. Now let's connect it back to the actual formula. We'll start with the simplest case you can possibly imagine, just a single lonely point charge.
So here it is, the equation. And it's pretty simple, really. The potential, V, at some distance r away from a charge q, is just that charge, q, divided by a few constants and that distance, r.
Let's use our landscape analogy to really break this down. First up, the charge, Q. That's the source. It's the thing that creates the electric hill in the first place. So a big positive charge, that's going to create a big, steep hill.
Next, you've got the distance, r. That's just your position on the landscape. Think of it as your coordinates on the map, telling you exactly how far you are from the peak of that hill.
And finally, V, the potential itself. That's the result. It's your literal elevation at that specific spot. Just a single number telling you the energy state at that point. No messy vectors needed. See how clean that is?
Okay, the analogy's great, but let's be real, seeing it work with actual numbers is what makes it stick. So let's run through a quick calculation to make this all concrete.
So let's say we want to calculate the electric elevation at a point that's 10 centimeters away from a 5 nanocoulomb point charge. First things first, we grab our formula. Next, we line up our variables. Q is our charge, 5 nanocoulombs. R is our distance, which, careful here, we've got to convert to meters, so that's 0.1 meters. And epsilon naught, well, that's just a fundamental constant of the universe. So now that we have all our pieces, all we have to do is plug them in.
And when you run the numbers and solve for V, look what you get. A single, clean number, 449.4 volts. That's it.
No x component, no y component, no weird angles to worry about. That right there is the power of using the scalar potential. But, and this is a big but, this elegant simplicity leads us straight to the single most common point of confusion when people first learn about potential. It's a fundamental gotcha that we absolutely have to talk about.
And the question is simple. If potential is just like elevation, well, where's ground level? What are we measuring all this height relative to? In other words, where is 0 volts?
Well, as the textbook points out, potential isn't really an absolute thing. It's always a potential difference. It's always a comparison between the point you're interested in and some other point that you just choose to call 0.
Let's go back to our mountain analogy for a second. We say Mount Everest is about 8,848 meters high. But high compared to what? That's not its height from the center of the Earth, right? No, it's its height relative to a reference point we all just kind of agreed on, sea level. Potential works the exact same way. It is always relative. So what's the sea level for electrostatics? Well, by convention, for lonely isolated charges, like the one in our example, we all just agree that the potential at a point infinitely far away is 0. And that kind of makes sense, doesn't it? If you're infinitely far away from the electric hill, your elevation should be 0. It's a simple rule, but it makes the math super clean and gives us a consistent starting point for all our calculations.
Okay, let's do a super quick recap of the 3 big ideas you need to remember. First, potential is your scalar shortcut. It's the simple way to describe the physics with one number instead of a complicated vector. Second, the landscape analogy is your best friend. Potential is just the elevation, and the E field, that's just the steepness of the hill. And third, and this is crucial, potential is relative. It's always measured from a 0 point that we choose, and for point charges, we almost always choose infinity.
And that leaves us with one final thought to chew on. We've described this whole electric landscape. We now know how to calculate its height at any point. So, what happens if we take a charge, place it on that landscape, and just let it go? What happens when it starts to roll downhill? Because that relationship between the shape of the landscape and the motion it causes, that's where the physics gets really interesting.